Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to have a look at the hydrogen molecule and see how we can solve the properties of this system with the use of Green's functions. And I'll take as a basis my two hydrogen atoms and a single s orbital per side, so that we can first have a look at a solution with the use of wave functions as we have done before, and then look at the solution with the use of Green's functions. So our hydrogen molecule has two hydrogen atoms. We have two sides, side 1 and side 2, and they sit some distance apart from each other. We'll take a basis of the 1s orbital per side. So state 1 corresponds to 1s at r is 0, and state 2 is the 1s at r minus a, and that is our vector a. Then we have our Hamiltonian, and that is just t times the hopping, where we annihilate the particle at 2 created at 1 plus creating at 2 annihilating at 1. Of course there is also an on-site energy, but that is just shifting the center of gravity of your Hamiltonian, and that doesn't really matter. You can think of hopping of a half t in this direction, hopping a half t in the other direction, such that this is a system with periodic boundary conditions. So we can look in Fourier space, and we have two k points in our system. We have k is equal to 0, where we create at 1 and create at 2 with the same phase. And we have the state with k is equal to pi, where we create and annihilate with opposite phases, e to the I ka, which is then plus minus. If you had 4 particles in a loop, it would be 1i minus 1 minus I for the possible phases that we have. So we can also write our Hamiltonian in k space as t times a dagger gamma minus a dagger x ax. And we know that our hopping matrix amplitude is smaller than 0. So we can look at our band structure as a function of momenta, which of course is discrete. We have two k points, gamma and x. We can have a look at the eigenenergies. At gamma we have energy t, at x we have energy minus t. If we look at the densities of states, then these are delta functions peaking at t and minus t. If we look at an energy level diagram, we start with two states, state 1 and state 2, with their energies centered at 0. Then they interact with each other, making the bonding. And the anti-bonding state, the state at gamma and the state at x. So we know what our eigenstates are, a dagger gamma 0 or a dagger x out of the vacuum, and we know what our energies are, t and minus t. So with that we have solved our system. Now let's see if we can do the same with the use of Green's functions. And our Hamiltonian is given as the hopping matrix element T times a matrix that allows you to go from state 2 to 1 or from 1 to 2. Our Green's operator is given as 1 over omega minus the Hamiltonian plus I0 plus. And this is nothing else than a matrix inversion, where we have omega plus I0 plus on the diagonal, and minus the Hamiltonian, also minus t, on the diagonal, off diagonal, and we need to invert this. So we can invert such a 2 by 2 matrix. You either remember how to do matrix inversion or you type it into Mathematica. And this is 1/2, 1 over omega plus I0 plus minus t plus 1 over omega plus I0 plus t on the diagonal. And on the off diagonal, 1 over omega plus I0 plus minus t times omega plus I0 plus t. And the matrix is symmetric. Omega plus I0 plus minus t, omega plus I0 plus t. Now we can look at our densities of states, which is minus 1 over pi, the imaginary part, vacuum, creating and annihilating the particle in a local state, which we can take 1. So that is just the left top element, minus 1 over 2 pi, imaginary part, 1 over omega plus I0 plus minus t plus 1 over omega plus I0 plus t is 1/2 delta omega minus t plus delta omega plus t. So we have 2 delta functions centered around plus and minus t. Exactly what we also had. We have eigenenergies at plus and minus t in our system. So we can calculate our Green's functions by inverting a matrix instead of calculating the eigenstates. Now for a 2 by 2 matrix, calculating the eigenstates or inverting the matrix are pretty much similar. For large matrices, especially because we do not need to know the full inversion but only the left top element of the inverse of a matrix, inverting the matrix can become significantly simpler than calculating all eigenstates. Now in order to calculate the band structure, we have to transform to k-space. For Hamiltonians that are periodic, that is basically diagonalizing your Hamiltonian. For Hamiltonians that would not be fully periodic because we have impurities or a surface, that of course is no longer true, and Green's function methods then still work, whereas calculating the eigenstates by the use of a Fourier transform would no longer work. But in this case we can just define the matrix that makes the Fourier transform. We have the state at gamma, where we have the same phase, and we have the state at x, where you have a different phase between the two states. And then we can calculate the matrix rotation of our Green's operator from real space to Fourier space. And what we find for the Green's operator in k space is omega plus I0 plus minus t for the bonding state at gamma, and 1 over omega plus I0 plus minus t plus t for the state at x. So we know when our crystal momentum is 0, comma, then we have a pole and omega is t, which is the eigenenergy. And when we have the k is pi over a, our x point, the antibonding state, we have a pole and omega is minus t. So also in k-space we reproduce the physics that we had before, that we can read off what the eigenenergies are in our system. Now what we can also do is have a look at the time evolution, because that's what our Green's functions in the time domain basically tell you. And our Green's function in the time domain, or the Green's operator in the time domain, is e to the minus I ht. And now t of course means time, whereas here t means the hopping. So let's set our hopping equal to 1. And if we then calculate e to the minus IH times the time, then we find that our matrix is given by cosine t minus I sine t on the off diagonal and cosine t on the diagonal. So if my wave function at time equals 0 is equal to a dagger 1, 0, which is creating the particle in the first state, then this is state 1, then psi t is nothing else as your Green's function times our vector, which is cosine t times state 1 minus I sine t times state 2. So we see that we get an oscillation between the particle being in state 1 and state 2. So if I have a hydrogen atom and I create an electron on one side, then it will move to the right, to the left, to the right, to the left, to the right, to the left. If you would Fourier transform this oscillation, then there are two oscillations that we have. That is the overall phase that starts to oscillate related to the total energy of the system. And we have the oscillation where the particle is moving from the left to the right. And these two frequencies will be exactly the frequencies that we have corresponding to the eigenenergies in our system. But in real space, this shows you as oscillations back and forward within the hydrogen atom. Well, this is of course an example where we can use Green's functions, but the advantages of the method do not really show, because you can also solve this in other ways. In the next set of lectures we will continue with cases where that is no longer the case, where the simple exact solution by just looking at the eigenstates is going to be problematic, but the Green's functions are still able to get you to solutions. And that is, for example, the case when we have impurities, or when you want to look at the surface of an otherwise periodic system. For now, thank you very much for your attention. We see each other in the next lecture. Stay healthy.